I work for Wallet.com, and I'm going to talk to you about some of the use cases we have, some of the things we try to achieve, and how Flink plays a role in that. So I'm going to talk about shopping, about having a conversation with your customer, measuring that, having cause and effect relationships, and how to build the end-to-end pipeline to do that. A short background on myself. I've been doing big data distributed processing for over 20 years. Have been using Hadoop for over 10 years. And over time, I've contributed to most of those systems. And I talk a lot at conferences. So if I go shopping, I truly hope there is a salesperson who can relate what I'm saying into the product that fits my needs best. And what that salesperson is really doing is they're trying to listen, they're observing what I'm doing, they try to understand that, they're processing that, attaching their knowledge of the product set to that, and what previous customers have done before. And based on that, they create a response. And this is something that happens over and over again, and they remember what I just said, what I asked and what I said. And that is very important, because if they were not to remember, the answer to the question, I want something to play with, may yield this answer. But maybe I was really looking for this, or even this. And what you want as a salesperson is the customer walks out with the product they are happy with. Because in the end, it all revolves around making money. That is in the offline world. And in the online world, we're trying to do something similar. We have a store, our web shop, with lots of products. Not really lots of products. And this is too much. This is too much for the customer to comprehend, but it's also too much for the salesperson to comprehend. There is no human salesperson that can actively advise you the best product for your situation. And to give you a bit of an overview, we have the over 22 million available products. In the backend, there are lots more. But we also have more than 10 million active customers, as in customers who actually purchased something in the last year, billions of page views, and millions of packages. But to have an online version of the conversation, to try to do the same thing online, we need to, first of all, be able to have accurate observations. We do not want to miss any kind of response from the visitor. We want to know what they did. And we have to have something to process that data in a low latency, scalable way, so it's quick enough, and it can handle at least something like 100,000 events per second, which is our reality. To remember what that visitor said, we need to be able to maintain state per session, because that is simply what's needed to have a successful conversation. And we need ordering guarantees. If you start mixing up the order from previous questions and answers, it becomes really messy. Looking at our stack, what we have today, to implement this, we have created a project we call Measuring 2.0, which is about tagging the content and doing the observations. We're currently working on what we call Understanding 2.0, which is like interpreting what is happening and a bit of the processing about what should we do next. We see a need for streaming data science, incremental models, something that I see in the data science community as something relatively new. And of course, we have something that creates the content, that takes the catalog and the analysis results and creates a new part of a page. So why do we have a new measuring project? Don't we already have tools like Omniture or Google Analytics? Well, measuring interactions about what the visitor is doing is all about what are we showing and how are they responding. Do they respond to the adverts, to the incentives, to the inspiration, or not? In addition to that, we want to have a measuring system that has a much broader application than just making a nice dashboard with how many visitors. We want to do all kinds of analysis, all kinds of data science to make our entire platform better. To achieve that, what we really need is to measure all details. What was on the entire page? Now, most of the standard web analytics solutions only measure the where, as in the URL and the timestamp, and sometimes they have the primary thing that's on the page, for example, a product. But more detailed than that is usually not the case. What we want is not only the where, but we want to know for every group of elements why it was there. For example, these are product recommendations for that one. And we want to know exactly what we put in there. We want to know exactly what product and what price and delivery, etc. options did we show. Looking at our volumes, we are in the couple of thousand pages per second range. Depending on the time of the day and the time of the year. Roughly 20, 30 events per page, also depends on the type of page, yields roughly 100,000 events per second. And our current reality is that we're doing about 3 terabytes of data per day, which we're processing in real time. Now, how do you measure such a thing? Well, the point is that measuring it with JavaScript, which is the common way of doing this, is fundamentally broken. You are measuring a side effect. You are not measuring the page. You are measuring the effects of a script that runs on the page. As a consequence, it's blockable. There are lots of visitors on the website that you do not see. And it's fragile. We have a lot of situations where we put a lot of stuff on the page, and if we put too much on it, the URL that gets sent to the measuring endpoint becomes too long, and you get this very rare URI too long error. And most of these JavaScripts are very locked in. They're part of a SaaS solution, Omniture, Google Analytics, and getting the data out is hard. And also, because of all this fragility, if you want to target an individual visitor, it's bad. It's really bad. Now, because it's locked in, we're also having a hard time to getting the data out. So in reality, it's old. You know, it's once every 24 hours we get the data. And this is useless inspiration. This is something I looked at yesterday. So what you really want is to help the customer, support them while they are still on the site. So the reality is that the value lies in having that data available in a very short time span. From measuring to being able to analyze it and use to improve the website has to be very short. Do realize that not every use case requires this short time span. If, for example, you are doing analysis on the click data, on crowd behavior, on how people move in groups, what kind of products are trending, those are the kinds of things where a micro batch or a batch situation is fine, because you're doing something not for the customer at hand, but for future visitors. If you're doing something for the customer you are trying to have a dialogue, a conversation with at this moment, then you need the really low latency. So you can understand, because we've been doing Hadoop and all the related tools for quite a while, we've been doing a lot of batch processing, MapReduce, Pig, Spark, all of those, we have those. But those are all the crowd-based analysis things. Nowadays, we're moving from our own data center into the Google Cloud, so we're also doing a lot of data analysis using Dataflow and BigQuery. And for the real-time part, for the last few years, we have been doing Apache Flink and Apache Beam to get the low latency things going. So I mentioned that it's a requirement to measure accurately. So how do we do that? If JavaScript is not enough, where then do you measure? Well, what we came to is that we measure where the thing we want to measure happens. This means that in most of the cases, we will be measuring in our data center, in the service that is responsible for the event at hand. So if we have a basket service, if you do an add to cart, that is the thing that says the event occurred. And also, this means that most measurements do not occur in the browser. Most events do not occur in the browser, so we don't measure them there. So your average page, we measure server-side in great detail what is actually in the page. And on the client side, we measure which fraction of the page is actually in view. Because pages are like this, screens are like that, and so you only see that part. And also things like screen resolution and stuff like that, that is measured in JavaScript, but that's the only place where you can measure it. Now, in the past, with tagging with Omniture and Google Analytics, we were measuring the orders using JavaScript on the order confirmation page. Now, in Dutch retail, there is a system called Ideal, which in general means that you go to the website of the bank where you complete the transaction. As a consequence, a significant percentage of the people do not return to the order confirmation page. So we have a lot of missing orders in the data. We do have them in the backend, but according to web data, they never occurred. So we listen to the order events in our backend, and we have a website ID in there to tag them to the rest of the events. And the order confirmation page measurement is now just viewing an order that was just placed. It's just a viewing event. In order to get the data accurate, we measure at the point where we built the page, where we built the response, what we actually put in there. So stuff like the product ID, what type of product, what price, what condition, what seller. We're a platform, we have a lot of different sellers. We measure them at the point where we built the page. Now, people have said, yeah, but if you have the offer ID and the product ID, you can later join them. Well, at our volume, this is already a problem, but also we have a lot of caching in the services. So if we at a later time say, what was the price at that timestamp, it may be that that visitor has seen the cached version from 2 minutes before, instead of the accurate one at that point in time. So later joining is not an option. I mentioned that the events had to be ordered. Yeah, but why is that? Well, if you have data which is like loose sand, no correlations, no ordering needs, you just need to like bundle them and count them like is common in normal web analytics, then it's easy. You know, there are no problems. But our use cases, in addition to having the conversation, are things like doing banner optimization. We show you a banner and you either click it or not, or A/B testing, or search suggestions, which I'll show a bit later, a bit more. But also attribution modeling. We show you an ad and you buy something, makes a difference in the ordering. And it all boils down to what I call behavior analytics, a cause and effects relationship between what we show and what you do. And that this ordering matters is also very simple explainable. If you click a banner and then buy a product, there is a probable cause between those two. It's a possibility that the banner actually helped in converting you into buy the product. If the order is reverse, it was definitely not. And this distinction is purely based on the ordering of these two events. Now, if I want to do an analysis like this, in computer science, the very simple model you can use to do that is called a finite state machine. Those are simple, low latency pattern detection models, but they expect ordered events. Now, in reality, the finite state machine is only states, and in my experience, you just about always need one class more advanced, which is the push-down automaton, which is essentially a finite state machine with a bit of memory. Same thing, very simple, very low latency pattern detection, and also expect ordered events. Now, to give you a bit of an idea what would happen if the events are not ordered, let's take a very simple example. I have a machine that can get hot, and if it gets hot too fast, it may be an indication of it blowing up, which I want to have an alert about very fast, or even a machine responding and turning off the power. And the way you would implement this is to say, okay, we have measurements, and if the change between two subsequent measurements stays within bounds, it's all fine. And you would have a very simple loop. Each time a new event comes in, you record it, you compare it to the previous one. If the delta is in bounds, it's fine. If I were to simply reorder the measurements and throw them like this, you have a lot of false positives and false negatives. You have a big problem. And in order to fix this, well, that is hard, and it takes time. The only real way to fix it is to have a buffer with a sense of the maximum out of orderness, which may very well run into the minutes. And if you want really low latency, if you want to be safe with your temperature detection, or you want to have a conversation with your customer, low latency is a must-have. And while we're at it, let's keep things simple. Exactly once really helps in keeping your application as simple as possible to make it work. So looking at it as a whole, we really are simply trying to never damage the ordering end-to-end. And to achieve this end-to-end ordering, we have to start at the measuring point, where we record what is actually happening, the transport and buffering and storage of the measurements on the way to the processing, and of course the processing has to support it. Now, if the measuring point, I simply say, if you have a single entity for which you want to record a time series, there should be only one system measuring it, a single measuring instance. Because if you have multiple, then at the technical level you would have multiple write buffers into the transport pipe with rate, and then you get timing differences and ordering problems. So in IoT, you see something like this. You have a single sensor and a single Raspberry Pi, and you're all fine. At bol.com, we are a website. We try to keep the visitor to a single web shop instance, so sticky sessions, routing the visitor to the single instance to achieve this. Do note, this is very hard, and this is not perfect, but we are trying. Currently, the view measurements and the orders are measured at a different point in our landscape, and those are sometimes a bit out, but because of timing effects, view measurements are always buffered in the browser, and orders are always delayed a bit because of all kinds of fraud checks and verification steps. This is not too much of a problem. So now we have great measurements, and we need to get them somewhere. So we need to transport them. And in order to do that, we want something that maintains ordering. Now in computer science, and for our use case, we need it per session. So not a global ordering, but a per session ordering. So we need something that is first in, first out. And in computer science, they call that a queue. And some systems I would call a partition queue. And a queue maintains order. And a partition queue, like essentially what Kafka does, is a collection of queues. Problem. If you go to the outside world and search for a queue, you get a lot of systems that are not a queue. In JMS, there is something called JMSQ, which is not a queue. ActiveMQ, not a queue. Google PubSub, they're nice in that respect. They're not claiming to be a queue, but they do have a very elaborate page explaining why you do not need ordering. I think you do, in some cases. Internally within bol.com a couple of years ago, because of performance and scalability problems, some people created our own queuing system. Same thing, it is not a queue. Now looking at systems that are queues, that support our needs, there are a couple. At least Apache Kafka, which is the one we use in production. That is a partition queue. There is Apache Pulsar, They're currently working on getting the Flink connector in Flink. There is Pravega, which is currently being beta tested. Looks very promising. And there's MapR that have an event store that you can use that also has these properties. Given that we are in the Google Cloud, the solutions by Amazon and Microsoft are in the wrong cloud for us, although they do also support these requirements. So within our company, we are saying, hey, if you want messages and ordering is not important and at least once is fine, then use PubSub. I call it a distributed set. It's a high I/O distributed set, not a queue at all. And if you need some ordering guarantees and preferably also exactly once guarantees, then use Kafka, because that is a queuing system. So now we have the measurements into the transport and we need to start processing them. So we said before, hey, in order to do these things, we have the low latency, exactly once ordering guarantees, and we want to have stateful processing by key, by session ID. So what kind of processing kits are out there? Well, the reality is that stateful processing kits, I've only found 2 at the moment, and they've been talked about a lot these days. Beam, it does the exactly once by deduplication, so it not really have the exactly once guarantees as a core design feature. Ordering is sometimes a bit flaky, and the keyed stateful processing is hard. The big advantage, and this morning in the keynote it was also said, Beam and all the Google tools are built around dynamic scaling. They see that as an operational challenge. So all of these tools have dynamic scaling. And I truly believe that this feature breaks all the other things that we need. And as a side note, I personally don't like the API, but that's personal. The alternative, Apache Flink, also does low latency, but also gives you exactly once, gives you ordering guarantees, which is inherent in the design of the framework because they use the Chandy Lamport system. It supports keyed stateful processing, not quite finished yet, but already very usable. And in contrast to what Beam supports, the scaling is fixed. So in order to rescale it, you have to do a snapshot, save point, bring it down, bring it up again with a different parallelism, which is, in some cases, not what you like, but that's a trade-off you're making. And I personally like this API better, but like I said, personal. And then you have to realize that changes happen. People come up with new requirements. They come up with new business requirements, new ideas, new wishes, and as a consequence, the data structure you're trying to pass from your measurement point into your processing gets new fields, and some fields get discarded, and okay, how do you handle that? And it's even worse. Looking at stream processing from a from an abstract point, you see that you have data producers and then some kind of streaming connection in between, and the consuming systems. And the real payload, looking at all of the APIs, is a byte array. You need to specify a byte array. And in addition to that, the producers, you want to have multiple applications providing data, or at least multiple instances. You want to do rolling upgrades. You want to do canary releases. Same at the consumer end. So you need something that can handle that. In addition, a system like Kafka persists the messages until the TTL expires. So the reality of a Kafka partition or a Kafka topic is that you'll have multiple versions of the same message in the same topic. So we need a system that is able to convert our data structures into a block of bytes that supports things like data types, default values, allowed values, nested records, and has bidirectional schema evolution. Because if you first upgrade the consumer or first upgrade the producer, maybe in a rolling fashion, it should keep working. Now, we have chosen Apache Avro for that. I'm also a committer and PMC for Avro, so it kind of helped. And I've adapted Apache Avro a small bit a few years ago to support this kind of use case much better. Now, Apache Avro, you can define a record structure in what is called the IDL. There's also a JSON format, but the IDL is much easier to use and to maintain. So this is a dummy example data structure. And from this, code is generated that allows you to do something like this. So you have all kinds of nice getters and setters to fill the structure that guarantee and guard all the requirements you imposed in the schema definition. And in addition, the comments you have used in the IDL are transported into the Java doc of the resulting getters and setters. So in your IntelliJ, you have a pop-up explaining what should go in there. Now, the thing I built a few years ago is the Avro message format. And it is a single record converted into bytes designed to support this streaming scenario. So the only real thing you need is a schema database, a schema registry. And the key is a 64-bit hash of the actual schema, which has been sanitized, so changes in the comments don't affect the hash. And that's essentially the only thing you need. So what you find in your Kafka topic is 2 bytes being the header, and then the 8-byte fingerprint, the hash of the schema, and then the bytes of the record itself. So the overhead is quite small. If you compare that, for example, to JSON, where essentially you're having like half of the schema in every record again and again, this is much more compact. Now, using that generated code in a system like Flink, you can do something like this. You have a serialization schema for my Avro-generated type, and then you can simply do 2-byte buffer and then extract a byte array from that. And then you have a serializer, and then in your actual code, you can do something like, okay, I have a data stream of these things, and I just have a Kafka sync, and I just write them out. Consuming it again is similar. You have to have a person deserializer, which is almost as simple, with one additional thing, and that it has to have an implementation so that it can find the schema in case it is confronted with an ID it does not already have. So you can use any implementation you like behind that. If you want to use a Kafka topic as a schema registry like we do, that's fine. If you want a database or a property file or whatever, anything goes. And then to use that in your application, you just have make it part of the constructor for the consumer, and it works. So this is essentially an end-to-end pipeline. So how would you then use that? What would a state machine look like? Now, on our website, one of the first things we built almost 10 years ago using MapReduce is our search suggestion application, which pre-computes for all letter combinations you type in a list of suggested terms. Based on a popularity ranking done by other visitors over the last weeks. And essentially, the algorithm looks at the search funnel. People search, and based on that, they find a product, and based on that, they maybe add it to a cart, and sometimes they even buy it. And we have said, hey, let's reverse the value of that. If you find something and then choose it and then buy it, it increasingly becomes more valuable. Now, mapping this into a streaming scenario, because we originally built it in batch, would look something like this. And this is oversimplified, let's be honest about that. So you could say you have the M2 data stream coming in, where you filter out all the events that are completely not interesting, and then you leave out the events that are sensible, and then you do an evaluation. Hey, which relevant events occur from this? And based on that, you can then say, I have a scoring mechanism where I say, hey, we found the word Harry Potter led to a product page. Then we say, okay, let's give that 25 as a score, for example. And then from that, we build a list of suggestions, a mapping from typed letters into a suggested term with the score, and then shove that suggestion delta into our database that is used for serving it on the website. It's good to realize that for this first part, the ordering is really important because there in the stateful analysis, the cause and effect analysis is done. After that step, the ordering guarantees are not that important anymore, because the scores are simply added together on a per record basis. You can even say, hey, you're buffering it to make writing into the suggestion database more efficient. So you buffer it and then write it once every minute or so. Now this state machine, like I said, simplified version, how would that look? Well, you can say you have an initial default state, which says, I'm not doing anything with search. And if you do something, you simply stay in there. And if you then do a search action, you search for X, then you go into the state searched. And as a consequence, the event goes out to the next stage in our flow. Hey, somebody searched for X. And that stage can then say, I'm giving this score to that. If you then go to a product page, same thing. Hey, somebody went to a product page caused by X. And X is essentially the variable we keep in memory. And then our product pages are actually a set of pages because we have product reviews and alternative prices and offers from different sellers. So you can stay within that. But if you then go to the add to cart, again, an event goes out, hey, we had an add to cart for the word X. If in any of those stages you do something different, you go back to the initial default stage where you're not doing anything with search. So this, although very simple, is a way we can do streaming updates of our search suggestions and make them throughout the day more relevant. And we have seen in experimental setups that really makes a difference. If somebody famous dies during the day, we no longer have to wait till the next batch run, somewhere in the night, to make our website more relevant for the visitors. So if this is useful for you guys, there are a couple of books I could recommend. There has been a signing session of the last one yesterday, so even the authors are around here. But the other two are also really well worth the read. So if you think this is a cool technology and you like living in the Netherlands, then don't hesitate to get in contact. And we have a website if you like that. So thank you for listening. Questions?
So about the state machine part, so when you say if nothing happened, it just stay there, do you mean that you just eat the event that goes into that stage and never do anything? Or what do you mean by never goes out?
I think I miss what you mean.
So basically...
you mean the search thing?
Yeah, this page, yes.
Yeah?
So you have a search event coming into your application. So you change the state to searched. Yeah. And then if you see another
you go to the home page, for example.
If you click on the page on one of the product page, then you know that the search result is actually satisfies user needs. So you basically said, okay, they found what they want, right? Yeah. And then you say, okay, in my state machine, I put the state of that guy into found. And if nothing happens, eventually, are you going to just, do a TTL, then change the state back to default no search, or?
The thing is, essentially, two things can happen. Either the visitor clicks on something else, and the something else can either lead to staying in that state, going to the next state, or going back to the default state. If the user does nothing because they have closed their browser, we have a TTL to expire that data.
Did you also maybe consider it looks like maybe what a Bayesian network would be maybe a good good things maybe to compare with your state machines? Did you try them as well?
No, we haven't tried those yet. In this presentation, this is intended to be an illustration of how you can approach this. Like I said, I see that there is a need for a new class of data science, streaming data science with incremental models. And as far as I go, any math is applicable to try out. If somebody says, I can do this better with a neural network or with a TensorFlow thing, I go like, yeah, sure, try it. You know, this is to lay the groundworks and to make the possibilities of actually doing this.
What do you do if a user has opened like few tabs in the browser? Like, do you treat them as separate sessions or what?
Those forked sessions, as I call them, what we have done in the measurements is that because of unique IDs, we have a very clear way of chaining the cause and effect in the data, and then it's up to the data science that comes after how they manage that. Looking at the raw data that comes in, they have the option of maintaining state per tab of the single session. At the technical end, we can do that. Like I said, here I've simplified things.
No more questions, I guess. Then thank you very much, Niels.
Thank you.